Okay, so for this particular question, we're going to be calculating both the engineering stress or nominal stress and strain and the true stress and strain. Okay, so stress and strain, you need to make sure that if they're asking for true stress, you calculate that, and if they're asking for engineering stress, you calculate that. So there is a difference. So for this situation here, just so we'll draw the picture, just so you can get an idea of what it looks like in your mind. I'm going to have to rub it out, but anyway, we go like this, and we've got a bar, and we're applying a load to it, and our force that we're applying is 60 kilonewtons, which we know is 60,000 newtons. And before we start stretching it, it's going to have a diameter of 20 millimeters. So the distance across this circle here is 20 millimeters before we apply the load. And then after we apply the load, so this is before load. And then after we apply the load, just before it breaks, it's going to be equal to 10 millimeters diameter. Okay, this is a diameter. This means diameter. Okay, so we need to calculate this as an area. Okay, to work out our stresses, be they stresses that are engineering stresses or true stresses. Now, for the engineering stress, we need the area that we calculate using a radius that we get from this diameter. So we need to halve that to get a radius. So that would be R equals 10 millimeters. And for our true stress, we'd have to use an R that's equal to 5 millimeters. Okay, so that's what you need to keep in mind when you're doing this type of question. Okay, for true stress and true strain. Okay, so that's the picture that you need to have in your head when they give you this type of question. They're stretching a metal bar that's a certain diameter and it's a certain length. So let's do our engineering stress and our true stress first, and then we'll do our engineering strain and our true strain. Okay, so get a pen here. Our engineering strain, I'm just going to call that just a normal strain symbol, is equal to force over A naught. Okay, A naught being the initial area before we do anything. Okay, so we know that that's going to be equal to the force, which is 60. We need to express it in newtons, so we'll say 60,000 newtons over our area. Okay, initially. So we know that we have a diameter of 20 millimeters. Okay, so our diameter D equals 20 millimeters. So R, a radius, because we know that that is a diameter across the circle. Half a diameter is our radius. Okay, we should know that. I hope we do. A radius is going to be equal to 10 millimeters. But we need to convert that value to meters. Okay, so we'll go 10 millimeters, and we should know that there's 1,000 millimeters in a meter. So we go 1, 2, 3, put the decimal point there, 0.001. So now we need to divide by the area. We know that the area of a circle is equal to pi r squared. Well, I hope we know that. So we're going to put that all over pi times 0.01 squared. Okay. We need to say 0.01 because we needed to halve this diameter. Okay. Now, when you do that in your calculator, so I would say 60,000 divided by, make my brackets, times this, square my value. You should end up with a very large number, okay, because it's going to be in pascals or newtons per meter squared. So you end up with a big value, and if you divide that value by either 1,000 to get to kilopascals or 1,000,000, you'll get a value. So I divided my answer by 1,000,000, okay, and I ended up with 190.99 megapascals. So that is our engineering, our stress engineering. Okay. So all we did was divide by the area before it's deformed by being stretched. Okay. So that's our answer. Okay, now if we want to work out our stress that's true, what do we need to do? We need to say force over area, but this time we're going to say 60,000. This is the newtons. This time we're going to divide by our area after it's deformed. So we end up with a diameter when it's stretched of 10 millimeters. So our R value is going to be 5 millimeters. So our area of our circle is pi times 0.005 when we convert it to meters, because 5 millimeters divided by 1,000 equals 0.005. We need to square our radius, and we end up with a true value. When we divide this will give us a value that's very large, and it will be in pascals or newtons meters squared. Newtons per meter squared. In other words, newtons over meters squared. I prefer to use pascals. That big value, if you divide it by 1,000,000, becomes a little bit more easy to work with, and it becomes 763.94 megapascals. Do the maths yourself and make sure you get the same values. So you can see this is a lot bigger, okay? And that's because if you look at the graph on the exchange page, your true stress is always larger than your engineering stress, okay? Or most times it will be in this situation. So that's a good way of seeing if you're on the right track as well. So just remember, engineering or nominal stress, use the original area, A0, before you stretch it. And for true stress, use the area after it's been deformed, okay? And that's how you work out your engineering stress and your true stress, okay? Have a go at doing this question, or actually I'll send you an email about this particular way of working, and you can maybe do a question of your own, or we'll do one in class. So there we have it. Now we just have to we've done stress, now we have to do strain. Now strain is about length, okay? Stress is about forces over area, strain is about lengths. Okay, so let's now work out our engineering strain and our true strain. Okay, so let's do our engineering strain first. So that's just the formula is change in the length, okay? Delta L, delta means change in length, over the original length. Okay, so we know that at the start, the initial length is 200, and at the end, it's 220. So if we go 220 minus 200, that's going to be delta L, okay, the change in length. So we end up with 20 millimeters. Okay, now you might be compelled to convert this to meters. As long as you convert both of them to meters, the answer will be correct. But because it's a ratio, as long as the units are the same, you will get the same answer. So for this one, we will have 20 millimeters. I'm going to leave it in millimeters, which means my bottom has to be in millimeters as well. 20 millimeters over the initial length, which is here, initial length, which we say is 0, okay? In other words, starting from the beginning. Okay, so 20 over 200. So E, that's millimeters. Our engineering strain is going to be equal to, we cross that out, divide by 2 top and bottom, 0.1. Okay, so that's how you do the engineering strain. And now all we have to do is work out our true strain. That formula is a little bit harder, okay? So that formula is equal to the natural logarithm, ln on your calculator, and then you take your length at the instant that it breaks over L0, which is the unstretched length, okay? So that's going to be equal to log of, that's the stretched length, which is 220, over the unstretched length, which is 200, and you should end up with a value, in this instance, is a little bit lower, okay? So in this instance here, you end up with 0.095 0.95. Okay, so not a lot lower, but it is lower. Okay, so strain true is equal to 0.095. So that's how you do this type of question. Hope that helps, and make sure you learn how to do this, because you will need it.